Hello guys, Zeus here, and today I'll be continuing Neon. Now, with that out of the way, let's get into it. Chapter 2, Neon and the Other Nobles. The ancient Greek philosopher Democritus suggested sometime around 400 BC that all matter is made of minute particles. He called these particles atoms, and they were the smallest possible pieces into which matter can be divided. The word atom comes from a Greek word that means which cannot be divided. About 2,200 years later, scientists realized that each of the elements, the basic substances that cannot be separated into simpler substances, no matter how much you bend, bang, heat, melt, or pulverize them, had its unique atoms. Their experiments also showed that the most important property of an atom is its mass, or weight. If the lightest element known, hydrogen, was given an atomic weight of 1, and all the other elements that had atomic weights that were close to being multiples of 1. In the mid-1800s, some scientists listed all of the known elements by weight and discovered that every eighth one was similar. So they attempted to arrange the known elements into a table that reflected this discovery. One of these scientists was the Russian chemist Dmitry Mendeleev, also spelled Mendeleev, who published his version in 1869. There were gaps in his table that he said would be filled as new elements were discovered. Because of the periodic similarities that cropped up every 8 atomic weights, he even made predictions about the missing element characteristics. The 3 gaps that he specified were all filled in the next few years, and elements that had filled those gaps had characteristics close to those he had predicted. Mendeleev's version of the table thus became the most widely accepted one. And he usually credited as the father of the periodic table of elements. However, it has been revised and extended considerably since the time. Scientists had learned that atoms are made up of subatomic particles called protons, neutrons, and electrons. Protons with a positive charge and neutrons with no charge form a heavy nucleus at the center of the atom. Electrons with a negative charge surround the nucleus in energy-specific shells or layers. The atomic weight of an element is determined by the total number of its protons and neutrons. The electrons are so much smaller than the weight that it doesn't matter much. Atomic weight is also called atomic mass. It is measured in atomic mass unit, AMU. The most common form of neon has an atomic weight of 20.1797 AMU. This number has been rounded to 2 digits, 1 in our periodic table, because it has 10 protons and 10 neutrons in its nucleus. Atomic weight is an average weight. Atoms of an element are not always identical. The atomic number of an element is simply the number of protons in its nucleus. Neon's atomic number is 10. Isotopes discovered. Elements can exist in a variety of isotopes. Each isotope of an element has the same number of protons in its nucleus, but a different number of neutrons. Neon played an important role in the discovery of isotopes. In 1909, Francis William Mason moved to the Cavendish Laboratory of Cambridge University in Cambridge. England, to work with Professor J.J. Thomson, who had discovered the electron in 1897. Thomson had developed a method of measuring atomic weights that involved using a combination of electrical and magnetic fields to cause positively charged particles to produce curves in the photographic plate. When Aston and Thomson experimented with neon, they saw two curves instead of one. This implied that the neon they were working with was actually made up of two different kinds of atoms that had the same chemical properties, but different weights. The first demonstration of the existence of multiple stable isotopes of an element. The most common isotope of neon is called neon-20. The mass number after the hypon is the total number of protons and neutrons in the isotope's atom. The second atom Aston and Thomson identified was neon-22. Today, we know there is also a third isotope that occurs naturally called neon-21. There's neon-20, neon-21, and neon-22. Aston and Thomson did not discover it because there's far less of it than the other two. Several short-lived radioactive isotopes of neon have also been created. Many radioactive isotopes have been made by bombarding naturally occurring isotopes of an element with neutrons or protons to introduce an extra neutron or proton in the nucleus. This can create an unstable version of the element that emits radiation and it transmutes or changes itself to a stable version. The radioactive isotope of neon currently have no commercial or scientific uses. Neon occurs naturally in three isotopes. Neon-20, the most common, has 10 protons and 10 neutrons. Neon-21 has 11 neutrons, and neon-22 has 12 neutrons. Periods and groups. Each of the energy levels or electron shells that electrons inhabit within an atom can only contain a certain number of electrons. The protons that make each element unique depend primarily on how many electrons in its outer shell, called valence electrons, are available to interact with the valence electrons of other atoms. Within each electron shell, electrons inhabit subshells, which scientists have labeled S, P, D, and F. The S subshell can hold only 2 electrons. The P subshell can hold 6. The D subshell can hold 10. And the F subshell can hold 14. Higher energy levels can hold more subshells. Energy level 1 has just 1 subshell. Energy level 2 can have 2 subshells. Energy level 3 can have 3 subshells. And energy levels 4 and above can have all 4. The rows of the periodic table are called periods. As you move across the period from left to right, each element has one more proton and one. Let's see. 5, 6, 7, and 8, 9. Where's the 10? 10. No, 11? Why are they called noble? Before people knew about noble gases, they heard of the noble metals. These are our metals like gold, silver, and platinum, but they don't react easily with other elements. Therefore, they don't really corrode or rust, unlike the base metals iron and copper. For example, they also tend to be very valuable. So they became associated with aristocrats or the nobility. Because there's already a group of noble metals in the periodic table, that it made sense that the new inert gases should also be called noble. They may also be called noble because, like nobility, they hold themselves aloof and don't mingle. Part of the periodic table of the elements is shown here. The noble gases, including neon, form the rightmost column or group. One more electron than the element on its left. There are 7 periods corresponding to the 7 possible energy levels. The columns of the periodic table are called groups. Each period ends in group 18, where the outermost subshell is full and adding one more proton and electron will start filling a new energy level. Period 2 ends with neon. It has 2 full electron shells. The inner one containing 2 electrons, on the outer one 8. Neon, like the other elements of group 18, are so-called noble gases. Has no electrons available for interaction and with other atoms. As a result, neon, like argon, krypton, xenon, and the rest of the elements in this group, are essentially chemically inert. Most elements of the particular group in the periodic table with certain expeditions have the same number of valence electrons and hence similar properties. In general, elements whose outermost shells are either almost empty, lithium for example, and which just has 1 valence electron, or almost but not quite full, such as chlorine, are the most reactive. The noble that wasn't. In 1999, a team of scientists at Lawrence Berkeley National Laboratory, Berkeley Lab at the University of California campus, Berkeley announced that they had observed element 118, temporarily dubbed Unicum and given the symbol UUO. And the decay products from targets to the lead bombards with an intense beam of high-energy krypton ions, Unicum would have fallen into group 18 below radon on the periodic table. However, in 2001, the team retracted its original paper because follow-up experiments at Berkeley and elsewhere failed to reproduce the results. The element 118 so far remains unobserved. Because the number of electrons in the element's atom is determined by the number of protons in the nucleus. Taking away or adding just 1 proton from the nucleus of an atom would turn it into a completely different element with completely different properties. Neon has the atomic number of 10. If you took away just 1 proton, you would have fluorine, a gas that, far from being inert, is highly reactive and dangerous. Neon is part of the atmosphere, and we breathe it harmlessly all the time. Fluorine gas is so poisonous that breathing it in a concentration of only 0.1% for just a few minutes is fatal. Fluorine is so reactive that under certain conditions, it will even form compounds with some noble gases, but not with neon. If, on the other hand, you add just one proton to neon's nucleus, you don't get a gas at all. Instead, you get sodium, a soft, silvery white metal that's so reactive it sometimes bursts into flame and plays on water. The first noble gas discovered, argon, posed difficulties for the periodic table. Evidence collected by Ramsay and Rayleigh indicated that if the new gas was indeed a new element, it had to have an atomic weight of nearly 40. That it was placed between potassium and calcium on the periodic table at that time. But there's no gap for it there. But the discovery of additional inert gases, first helium and then krypton, neon, then xenon, it became obvious that a whole new group was needed to be in the periodic table. Argon is not placed between potassium and calcium in the modern periodic table, because today's table is based on atomic number, not atomic weight. Argon, whose atomic number is 18, instead appears between chlorine, atomic number 17, and potassium, atomic number 19. Currently, Ramsay has the honor of being the only scientist involved in the discovery of almost an entire group of the periodic table. He did not discover radon, the heaviest gases in the group, but he did help determine its atomic weight. Ramsay won the 1904 Nobel Prize in Chemistry and Renegation, according to the Royal Swedish Academy of Sciences, of his services to the discovery in the inert gaseous elements in the air, and his determination of their place in the periodic system. Chapter 3. There's something in the air. Someday we may run short of certain substances, oil for instance. As the raised supply of them is used of, neon isn't one of them. There are other substances whose collection, use, and disposal poses huge environmental problems. For example, oil. Neon isn't one of these either. Neon, as noted earlier, was first discovered in the air. It makes up around 18 parts per million of the atmosphere. That means there isn't very much of it in a very large volume of air. On the other hand, there's a very great deal of air on the planet. So worldwide, there's more than 72 billion tons, 68 billion metric tons of neon. It's even rarer in the Earth's crust, where it makes up about 70 parts per trillion. It's the 82nd most common element in the crust, which is another way of saying it's extremely rare. Neon is actually rarer on Earth than it is in the rest of the universe. And the universe as a whole is the 5th most abundant human element in the atmosphere. That's because neon is produced in stars much more massive than the sun as a part of the process of nuclear fusion, a process in which the nuclei of two lighter elements are united to form a heavier nucleus with the release of large amounts of energy. Since neon is all around us in the air, when we want pure neon, that's where we get it. Although we had to liquefy the air to do this. In fact, we get neon from the air using essentially the same method that Ramsay and Travers used to discover the element. Carl von Linde, a German engineer, invented a method of liquefying air and separating out its components. German engineer Karl von Linde found a way to liquefy air in 1895 by first compressing it and then letting it expand rapidly. When gases expand rapidly, they cool. In this case, they turn the air into liquid. 1902, Linde figured out how to separate air main compounds, oxygen and nitrogen, by slowly warming liquid air. Oxygen and nitrogen boil off at different temperatures and can be extracted as they do so. But so do argon, neon, krypton, and xenon. For Linde, there were a little more than waste products. He was mainly interested in oxygen, which was needed in alkali torches for cutting and welding metal. Today, however, these waste gases are often extracted for various industrial uses. Neon's boiling point is so low at negative 410.94 Fahrenheit, or aka negative 246.08 degrees Celsius, that it doesn't condense into a liquid with the air. Instead, it remains as a gas, mixed with helium, the boiling point of which is even lower. And some nitrogen, by increasing the pressure, reducing the pressure, the nitrogen can be removed. It condenses back into a liquid and can be absorbed in a highly cooled charcoal. The neon is then separated from helium by using highly cooled activated charcoal. Both gases are absorbed by the charcoal. Then they release at different temperatures as the charcoal is warmed. It takes 88,000 pounds, 40,000 kilograms of air to produce 1 pound, 0.45 kilograms of neon. Nevertheless, neon is relatively inexpensive, costing about $7.60 per gallon, $2 per liter. There's no danger that we'll ever run short of neon. Only a few tons of it, on average, are used commercially in a year. In addition, since it's chemically inert, almost all neon used commercially will eventually find its way back into the atmosphere unchanged, ready to be extracted again. The fact that it's chemically inert also means that neon is not a danger to the environment, although it can be dangerous to those who work with it. Liquid neon is so cold and that contact with it can cause severe frostbite. Neon is not poisonous, but it can't support life either. Liquid neon, when it turns back into gas at room temperature, 68 degrees Fahrenheit, 20 degrees Celsius, expands 1,445 times the most of any known liquefied gas. If this happens in an enclosed space, the expanding neon can quickly drive out most of the air. They say the neon lights are bright on the Broadway. They say the neon lights are bright on Broadway. It is the first line of a song by Jerry Lieber and Mike Stoller that was made popular by Drifters in 1963. The main industrial use of neon is in neon lights. Long before there were neon lights, people knew that you could make gas glow. As early as 1675, Francis Ramster Dean Pickard noticed that when he shook a mercury barometer tube, it glowed faintly. Pickard didn't know why. But today, we know that static electricity was causing mercury vapor in the tube to light up. By 1855, a German glass blower named Heinrich Glaser was making glacier tubes. Electricity was applied to low pressure gas that were simply air, but other gases such as neon were used later in the tubes. The tubes would glow. Different gases produce different colors. In the 1890s, U.S. inventor Daniel McFarland Moore developed a light that consists of a glass tube filled with carbon dioxide and nitrogen. Electrodes at both ends of the tube pass a current through the gases, causing them to glow bright white. The gas inside was consumed quickly, giving the tubes a short lifespan. The Moore invented an automatic refilling. The bulb above contains a tiny amount of neon gas, so you shuffle your feet on the carpet, photo 1, while holding one of the bulb wires. Photo 2. Photo 2, then touch the other wire to a ground point like a water pipe or a metal file cabinet. Photo 3. You should see a brief flash in the bulb. That's the static electrical charge you acclimated by shuffling your feet passes through the neon gas, exciting it and causing it to glow. Refilling valve that could refill the tube during operation. If its pressure dropped, the first luminous advertising sign using more lamps, went up on a hardware store in New York, New Jersey in 1904. After Carl von Linnaeus figured out how to liquefy air and thus made it easy to produce inert gases, French inventor George Claude began experimenting with them in the hope of improving the Moore lamp. He reasoned that the gas in a Moore lamp didn't last because of reacting to electrodes at each end of the tube. If that were true, then inert gases should last longer because it wouldn't react with anything. Claude found that the neon glowed brighter for less electrical input than any of the other gases he tried. First, he displayed his neon light in 1910. And that's it for today's video. Hope you guys enjoyed, and I'll see you again very, very soon. Later.